Welcome to the Space Telescope Public Lecture Series. Tonight's talk, The Enigmatic World of Brown Dwarfs, Failed Stars or Errant Planets, by Elena Manjavacas of the Space Telescope Science Institute. I'm your host, Dr. Frank Summers from the Office of Public Outreach. It is my pleasure to join you each and every month, although I'll note that this month I am joining you not from my home in Baltimore, but live from the American Astronomical Society meeting in New Orleans. This is the week of the year when the world's astronomers gather for the AAS winter meeting, and I am hosting from my hotel room in New Orleans. And so I definitely have to say a wonderful thank you to Thomas and Grant, for they're the ones taking care of all of the technical aspects of this talk. Upcoming talks, well, you will find out that there are two that are still TBD. Both February and April are TBD. February, I actually had to hold out because we have the total solar eclipse talk going on in March, and could have been February or March, so I didn't schedule February, but when I get back from AAS, I will schedule that, and it'll get posted on our website. But March is the one you're going to want to hit. Because we have a total solar eclipse in April that travels across the U.S., starts in Texas, goes out through New England. Michael Kirk, a heliophysicist at NASA Goddard Space Flight Center, and John Maple, an outreach education person at Space Telescope, will give you all sorts of information about eclipses, how you can watch this eclipse, and some of the activities related to the space telescopes that we work on. But for the February 6th and the April 2nd, those are still TBD, and I'll work on those later this month. When they are scheduled, they will appear on our website, www.stsci.edu/public-lectures. Also on that website, you can find links to our webcasts, both in the Space Telescope archive as well as on YouTube. And if you would like to sign up for our email list, we send 2 emails, maybe 3 emails a month. You can sign up by entering your email address and hitting that wonderful subscribe button. On that website, as I said, will be the list of the upcoming lectures, and each lecture gives you the information about the title, the description, and after it's been recorded, the links to the recordings. Emails, as I said, sign up at our website. An alternate way to get notifications is to subscribe to our YouTube channel. That's youtube.com. Hubble Space Telescope is all one word. You'll get new video notices and reminders of live events such as these. And finally, if you have comments or questions, you can send them via email to publiclecture, all one word, at stsci.edu. You can also follow us on social media. We do social media for the Hubble Space Telescope, for the Webb Space Telescope, and for our institute on Facebook, X, YouTube, and Instagram. I myself don't do much social media. Oftentimes it's just advertising these public lecture series. I'm on Facebook, X, and they gave me a Blue Sky account, which I will honestly say I've only used 3 or 4 times. So I'll get into that. It's 2024. Maybe that's one of my New Year's resolutions, to see what Blue Sky has to offer. All right. So the news from the universe for January 2024. And since I'm at the AAS meeting, I didn't have time to prepare extensive news stories. So I just took the holiday gifts from the STSCI news team. And generally, we put out a holiday press release of an interesting image. And this year was no exception, and we did one for Hubble and one for Webb. So the Hubble holiday news image I'm calling "Good Things Come in Small Packages." Now, when we think of galaxies, this is one of my favorite galaxies. It's the Whirlpool galaxy, all right? And it's this grand design spiral, and it's just gorgeous, and it's 100 million pixels of Hubble goodness in this image. Or you might think of something like the Sombrero Galaxy, which is this big disk with this giant elliptical shaped thing. Oh, just stunning. Or then there is the galaxy Messier 82, which has this large disk and everything, but also has this blowout in the center. And these are all large galaxies. But large galaxies are not the norm in the universe. They are the norm in our heads, but most of the galaxies in the universe are actually small galaxies. And small galaxies can look beautiful too. A bunch of years ago, probably about a decade ago, we put out this wonderful image of a dwarf galaxy called 1 Zwicky 18. All right, and look at all those wonderful structures. And actually, the dwarf galaxies can have amazing structures because they're small and and there's not so much mass to sort of regularize them. They can be what we call irregular galaxies. So, for our holiday image for Hubble, we put out another dwarf galaxy, and this dwarf galaxy I find very pretty. It is UGC 8091. All right, and what's kind of fascinating about this is it's mostly just stars. It's a great big ball of stars, and to someone, this sort of looked like a snow globe, right? You know, you've got this big cluster of stars. This is, you know, I don't know. It's a relatively small galaxy. I can't imagine it's more than 1 billion stars here, or something like that. And you've got a little bit of nebulosity, but yes, this is large enough to be qualified as a galaxy. And it's nice, just really soft, a galaxy that you know, is sort of typical of the small galaxies in the universe, that they can have all these structures. They can have lots of gas. They can have very little gas. They can have lots of star formation. They can have already formed almost all of their stars and look, you know, pretty much like a dwarf elliptical galaxy here. So that was our Hubble holiday image. For Webb, we're going to call it running rings around the planet. All right, and the planet we are talking about here is Uranus. And in my mind, since the late 80s, this is the image that I think of for Uranus. This is the image taken by Voyager 2 when it flew by in the late 1980s. All right, and Voyager 2 is the only space mission that has visited Uranus. So this is the only close-ups we've really ever gotten. But we have gotten good images as well, because as ground-based observing improved, and as infrared detectors improved, we could get some pretty cool things, such as this from Palomar Observatory. This is observing in the infrared, and it's a series of images put into an animated GIF, and you can see the rotation of the planet, and because you're looking in the infrared, you can actually see more detail in the atmosphere. You can also, if you look at the very top and the very bottom, see something that's sort of reddish, right? That's a ring around Uranus, okay? This planet also has rings, but they don't show up in optical like Saturn. They only show up in the infrared. And if you want to see that ring in more detail, well, Hubble got you there. Hubble has some infrared capability in the near infrared, and this is an image from Hubble that shows the ring very clearly, along with some of the storms in its system. However, if you're looking in the infrared to look at Uranus, do you want to use Hubble? Sorry, folks. No, you don't want to use Hubble. You want to use Webb. So this year's holiday image is Webb's view of the planet Uranus. And that's detail in the ring system. It's kind of stunning compared to what we have known before, right? Where you'd get these tiny little rings and such, and now you've got full detail, amazing detail in the ring system around Uranus, as well as these little dots around here are not just random dots. Some of them are moons of Uranus, so that we've got detail of the Uranus system of rings and moons from the Webb Space Telescope. And I guess that sort of resembles a holiday wreath to someone. So they suggested it as the Webb holiday image. So happy holidays from Hubble and Webb. All right. Our speaker tonight is Elena Manjavacas. And come on, where are you? Thank you. There we go. I have to stop my share. Welcome, Elena. She comes to us, and she's from ESA. You can see she's got her ESA shirt on. So she's an ESA astronomer at Space Telescope. One of the great things about working at STSCI is its combination of, the folks here in the U.S., but also we get a lot of ESA astronomers coming in. That's wonderful. She originally comes from Spain, where she did her PhD at Madrid. And then she went on to do her, was that your undergraduate or your PhD?
My undergrad.
Sorry, I got my notes are slightly wrong here. Undergraduate in Madrid, and then you did your PhD in Heidelberg at the Max Planck Institute for Astronomy. Yes. Then she did postdocs at Tenerife, the Canary Islands, which I got to visit once. Actually, I was doing a lecture on a cruise lectures on a cruise ship, and we stopped in the Canary Islands, which was wonderful. And then also in Tucson, Arizona. And she has been, she was an astronomer with the Keck Observatory before coming here to Space Telescope. She's been here for 3 years and works on the near spec instrument team, which is the near infrared spectrometer on the Webb Space Telescope. As you will find out tonight, her specialty is brown dwarfs. But when she's not doing astronomy, she tells me that she does dance and that she does Oriental dance. She's traveled all across the world to do her astronomy, and she's here tonight for us. So, Elena, please turn on your screen share and welcome to the public lecture series.
Thank you very much. Thank you, Frank, for this wonderful presentation. I'm going to share my screen now. Please let me know if you can see my screen now in a minute.
Everything looks good.
Perfect. All right. Thank you very much, Frank, for this opportunity of presenting my research, which is my favorite topic of the world, brown dwarfs that I've been working on for more than 10 years since I started my PhD. Now I have the pleasure to be doing as an astronomer at Space Telescope Science Institute with the best instrumentation that we have in the world as astronomers. So today I'm going to talk about the enigmatic world of brown dwarfs. Are they phase stars or are they errant planets? And this is a dichotomy that has been going on since brown dwarfs are known, since the mid-90s. But first of all, I would like to introduce myself a little bit more and tell you how I got to study brown dwarfs and why. As Fran mentioned before, I was born in Spain, but not in any random place in Spain, but in a very small town in La Mancha, which is a very rural area. And because it's a very rural area, it's very dark in the night. So as a child, I had the pleasure to be able to see the sky, to see the Milky Way as you see in this picture. And that really inspired me to ask me a lot of questions. As a child, I would always ask me questions about everything. But the sky was something fascinating. And I was very lucky as a child to have very good teachers at middle school. And I was probably 8 when my teacher told us about astronomy. Told us that the stars that we see on the sky were actually suns or similar to our sun in a sense. And this was the mid-90s where exoplanets were not known. But he mentioned that was like a research topic that was going on back then, and that people were trying to find planets around other stars, so around the stars that we see on the sky. Well, since that day, that topic got me obsessed. And up to date, this is what I've been studying for my career. Exoplanets, brown dwarfs, which you will see later, they are very, very similar. They share many commonalities. They have many commonalities, and that's why I studied them. But yeah, as a child, in the mid-90s, the solar system planets were the only planets that were known, and that were the only planets that were known from the ancient times, from the Greeks until the mid-90s. until 1995 specifically. So just as a little reminder, these are the planets that we have in our solar system: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, that Frank was just talking about, and Neptune. And of course, at the school, I was also studying Pluto. But to please the International Astronomical Union today, I'm not going to show it here. And I want you to keep a couple of numbers about the stars, the planets of the solar system. One of them is that Jupiter, which is the most massive planet in our solar system, is 300 times the mass of the Earth. So it's 300 times more massive. And Jupiter is 1,000 times Jupiter. The Sun is 1,000 times Jupiter. So those two numbers for you to keep in mind. When I'm going to talk about brown dwarfs, I'm going to always compare them to Jupiter. But I also want you to compare the Sun to Jupiter so you see how much smaller, how much less mass Jupiter has. So when I started growing up and, of course, studying more astronomy, I discovered that actually the Sun was not only like all the stars were not like the Sun. Sure, the Sun is the most typical star that we find out there, but there are also other stars like that go from this is the spectral classification, what we call of stars. We have basically letters, and each letter refers basically to the temperature that they have. So the O stars are the hottest stars, 50,000 Kelvin. And we go all the way down to cool stars that are the M dwarfs or M stars that are about 2,300 at the minimum. So the Sun was kind of sort of in between, but it's, as I said, one of the most common that we see out there. And the coldest and the least massive stars that we knew also back in the day, I'm talking about the mid-90s, it was M stars. They were actually, as I said, pretty cold already, half of the temperature of the Sun. And also, the mass was pretty low. So 80 masses of Jupiter. Remember that I said that the Sun is 1,000 Jupiter masses. So the least massive stars that we knew were like about 80 Jupiter masses. So pretty light stars. So coming back to the general picture that we had in the mid-90s about astronomy, we knew stars, right? Like our Sun, like M dwarfs that were the least massive stars. And then the only planet we knew until the mid-90s, until 1985, was Jupiter. Jupiter mass. And there was this problem in which, in between Jupiter and the least massive star that we knew, there was no objects, right? So there were no objects known that had a mass in between Jupiter and the least massive star. No 50, no 30 mass Jupiter object, nothing. So it was weird. It's like something is missing. It seems like nature is missing something. Well, of course, nature is not missing anything. Nature is complete. But we did not find what it was in between. Of course, astronomers thought that there had to be something in between. And those are brown dwarfs. Brown dwarfs that nominally have masses between 13 masses of Jupiter and 80 masses of Jupiter. So any object with a mass bigger than 80 masses of Jupiter is a star. Any object with a mass lower than 13 Jupiter masses is considered a planet. Now, this is the nominal definition that has a lot of open questions here, there, and I will talk about some later. So, Theta 1 was one of the first brown dwarfs discovered in 1995 by the Spanish team. And Gliese 229b was the other brown dwarf discovered also in 1995 by the American team. So these were the first two brown dwarfs that basically were the first, the first discoveries. And then with time, as years passed, we discovered that there were many L's and many T's and many Y's. That is the spectral classification of the brown dwarf. So basically, more brown dwarfs and more brown dwarfs continue to be discovered. And what we discovered is that not all brown dwarfs were the same, but similar as stars, they also have their spectral classification. What is a spectral classification? It's basically the chemical composition that they have. So all of them were brown dwarfs, but the chemical composition was divided in three classes. The L, that were the warmest brown dwarfs, the T, that are a little colder, and the Y brown dwarfs. The Y brown dwarfs are super, super cold, with temperature down to 300 Kelvin, or even less, as I will show later in the talk. So, all right, now we know that brown dwarfs are in mass in between stars and planets. But how are they different from stars? Why are brown dwarfs not stars? Well, for that, I will go to the beginning of the story, of every planetary system, of every star out there in the universe. Starts with something like this. This is an image of the raw Fuki star-forming region. Of course, this is an image of Webb that was released in July due to the first anniversary of Webb. And this is a star-forming region because we see that there is like the colorful gas that you see here is hydrogen gas, most of it. And there is also dust. And what is happening here is that these areas are actually quite dense. So what happens is that they start collapsing. And they start collapsing by gravitationally collapsing by forming a disk. So if we zoom in any of these stars that you see here, I'm going to do a kind of fake zoom because we actually don't have the actual zoom image. We zoom in one of these stars. I'm just taking this one as an example. What we will see is like a star that is getting formed in the very center, and around it, it will have a disk. So it will be something like this. This is the disk, and in the middle of the disk is the star that is forming, right? So the disk will be collapsing, and it will form the star. And what happens when the star is forming? That the hydrogen is starting to fuse in the center. Brown dwarfs now form in the same way. Similar image, similar video. But the problem is that the part of the cloud in which the brown dwarf is formed doesn't have enough mass to actually start fusing hydrogen. So basically, in a star, the cloud where it's formed is dense enough that when it collapses, it starts the hydrogen fusion. And in that hydrogen fusion, you release helium and release energy. And that's how stars get the energy from. That's why the sun is giving us energy. But brown dwarfs cannot do that, even though they form in the same way, in the same disk, right? And actually, after you form a star, what you find, this is especially true for very young stars, is that because they form from a cloud, from a disk, even when the star is already formed, there is some remaining of the disk around the star. Well, the same happens to brown dwarfs. The brown dwarf has already formed, but there is still some remaining of the disk around. So in that sense, brown dwarfs and stars seem very similar. But the main difference is that stars can sustain hydrogen fusion, but brown dwarfs cannot. So brown dwarfs, basically, they maintain the heat they have since they were born, but that heat is just, it will be basically going out, will be disappearing as the brown dwarf cools down with time, because there is no chemical reaction that is keeping the heat or keeps generating heat. So basically, they dim down with time, and at some point, they kind of disappear, not disappear, because physically they are there, but they get cold, super cold. All right. Now we said the brown dwarf is in between stars and planets. Now we know the difference in between a brown dwarf and a star. But then what is the difference between a brown dwarf and a planet? Well, again, we start from the same picture. As we can imagine, when you form a star, I said there is a disk around it, right? And in this disk, not all the material is used to form the star. So there is some material that is kind of remaining. So the star has already formed, but there is remaining of material around. What happens to that material? Well, that material can actually collapse itself and form planets. This is exactly what is happening in this video, in which The star is in the center, it has already been formed, and then the material of the disk is collapsing and is forming the planets. And this is what has been happening here. I'm gonna play it again, just because it's a cool video. And that's how you form planets. What does it mean? That to have planets, you need to have a star. So stars and planets are gravitationally bound. In contrast to brown dwarfs. Brown dwarfs, in general, they are not gravitationally bound to any star, right? So brown dwarfs are errant, or at least most of the brown dwarfs that we know are errant. I will show you now some exceptions. So they are found in installation. They are not orbiting any other star. And that's one of the main differences between brown dwarfs and stars. And planets do not have disks. They form from a disk, but they don't have disks themselves. And that's also a difference between brown dwarfs and planets. But are really all the brown dwarfs isolated? Of course, astronomy is not an easy topic, and brown dwarfs couldn't be an exception. Well, actually, this is an image of the first brown dwarf that was discovered by the American team, that is Gliese 229b. And when astronomical objects have a name and have a B, C, D, E, that means that they are companion to something. They are gravitationally bound to something else. And in this case, the first brown dwarf, Gliese 229b, is bound to a star. So the first brown dwarf that was discovered, as you can see in the Palomar Observatory image from 1934 or the Hubble image in 1995, is orbiting another star. Not the only one. We have this very, very, very famous system that is VHS 1259b, that is a brown dwarf companion to a binary star. So brown dwarfs can not only be companions to stars, but also to binary stars. And actually, this brown dwarf is very particular because it has a relatively low mass. It's below 20 masses of Jupiter. Now, what is true is that brown dwarfs, usually when they are gravitationally bounded to a star or to a binary star, they are farther from the star than planets do. Planets are usually much closer to the star than brown dwarfs. And that's why we were able to resolve some of the brown dwarfs, to see some of the brown dwarfs, because they were pretty far away from the host star. If they were very close in together, it would be more difficult. And I'm going to show you some images showing how difficult it is actually finding stars finding planets around the stars, just using the light image. So yes, not all brown dwarfs are errant, but the great majority are actually errant. And just to make things more interesting, we have this other brown dwarf that is WISE 0855. This one is not gravitationally bound, so it's not connected gravitationally to any other star. This one is isolated, it's errant. This is the coldest brown dwarf that we know up to date, and it has a temperature of 250 Kelvin. That's the temperature of Earth. That's very cold. Jupiter has a temperature of 125 Kelvin. So this brown dwarf is very, very cold. And it has a mass between 3 and 10 Jupiter masses. So as you can see, it's below the limit that they said when I said at the beginning of the talk. This is the nominal limit of mass for brown dwarfs. It's like between 13 and 80 Jupiter masses. Well, this brown dwarf, Y0855, has a mass below 13 Jupiter masses. So is it a planet? But it's actually errant. It's by its own. Is it a planet? Is it a brown dwarf? This is an open question in the community, actually. Some astronomers call them planet, free-floating brown dwarf, free-floating planet. It's an entire debate because it's very difficult to know how it was actually born or what happened to it, right? So I personally call it brown dwarf, But yeah, there is the debate out there of people that don't know how to call it. Brown dwarf is a planet, it has planetary mass. So we see that brown dwarfs are kind of confusing because there are so many types. Some are bounding, some are not bounding, some are very cold, some are very hot, as hot almost as a star. So why do we make our lives so complicated and go ahead and study brown dwarfs at all? This seems like a difficult business. Well, actually, the answer is planets. If you like astronomy, and if you have been following other astronomy outreach talks out there, you probably are familiar with this little video. That is basically a combination of images of this planetary system that is called HR 8799. And it has 4 planets, B, C, D, and E. These planets are actually pretty hot. They are about 1,000 something Kelvin, so pretty hot. And these 4 planets are orbiting a star that is in the center of the image. And what happens to these planets? As I said, these planets are pretty hot. They are as hot, that hot that they overlap with the temperature of brown dwarfs. And actually, we can actually see how that happens. And I'm going to show just a plot. This is the only plot I'm going to show in the entire talk, but I really need to show it to show how similar brown dwarfs and some planets, particularly those that are giant planets that didn't image exoplanets, as these ones that we see here. And for that, I'm going to use this plot, which is called the color magnitude. It's not a color magnitude diagram as we have for star, it's a color magnitude plot. And in this plot, all the colorful points you see, they belong to some brown dwarfs. And what we are representing here is the magnitude or the absolute brightness of brown dwarfs versus the colors or the difference in brightness in 2 colors. So in the x-axis, what you can see is the J and the H color. Instead of J and H color, you can imagine blue and red. The difference on brightness in those 2 colors in a random image. So this is a plot that we are doing here, and we are measuring these colors and the absolute brightness for all these brown dwarfs. The L brown dwarfs are the hottest brown dwarfs, almost with temperatures going up to stellar temperatures, 2400 kelvins. Then we have the LT transitional dwarfs. Those brown dwarfs, I can do a whole talk about the LT transition brown dwarfs because they are very interesting. And then we have the colder T dwarfs down here. And if I do similar, if I measure the similar brightness and similar colors for planets, as the planets that I showed you before in the video, the HR 8799, this is what happens. And it's like, oh, look at this. It seems like some planets have actually very similar colors to brown dwarfs. That's why they are together in this plot. And that's very interesting because that means that if they have similar colors, probably they are very similar kind of objects. And that means that brown dwarfs can be useful to study exoplanets. But what is the advantage of studying brown dwarfs? As I said, most brown dwarfs are errant. They are by themselves. So there is no star contaminating the light of your object. If I go back to this video, you might think that this was easy to do, but nothing at all. Actually, what you have in the middle is a star, right? You actually see the symbol of the star in the middle. And why can't we see the planets that are around the star? Well, the first thing astronomers had to do is to use a coronagraph. A coronagraph is a device that you put on an instrument, that you put on a telescope, and that actually what it does is an artificial eclipse of your star. So it's like the solar eclipse that is going to happen in April, right? That's a natural eclipse. This is an artificial eclipse, and the coronagraph does this eclipse. But not only that, since these images are taken from Earth, we have, of course, the Earth atmosphere, that basically blurs all the image, and you need to correct it. And for that, you need adaptive optics, which is a difficult thing to do. All of that has been going on in this image. Of course, you don't see any of that. It would be nice to see the before and after, to see how difficult it is to get to this from an image that you would take with any telescope from Earth. So once you do all that processing, you end up seeing the 4 planets, the 4 HR 8799 planets. And still, they are pretty isolated, but still you can see that around the star, there are some bright points that we call speckles, that are basically due to that we have the Earth's atmosphere out there, and that of course that the light of the star is not completely blocked. The thing is that these speckles or these bright points around the star can mimic other planets. So there has been cases of people that think they found a planet around a star by direct imaging, and it was one of these speckles. So it's challenging. It's challenging, right? The observations of directly imaged planets are challenging, are very difficult to do, are very costly. But observing brown dwarfs is easy because you don't have the problem of removing the star. You don't need to remove the star. The brown dwarf is all isolated by itself. So it's great that they are so similar to exoplanets, because you just can go to the brown dwarfs that you think they are going to be more similar to the exoplanets you're interested in and study those. All right, that's very good. But how do we study brown dwarf atmospheres? And here is when the near-infrared astronomy comes into place. And with the near-infrared astronomy, of course, the James Webb Space Telescope. So astronomers, we cannot, we are sort of like experimental scientists, but we cannot go into a lab, take a star in a lab and put it and, look it through, I don't know, take a sample of the star and analyze it. We cannot do that. Stars are so far that, of course, even if we could go there, it's impossible to take a sample from a star. So how do we study stars? They are so far. Well, the kit for that is studying their rainbows, or also technically called spectroscopy. The rainbow. You have probably seen many times that you have a glass, a prism, and the sun is going through that glass or that prism, and you see the full rainbow of the sun, right? With all the colors from the ultraviolet to the red. Actually, yes, you see all the colors, but I'm going to talk about the colors that you don't see later. You see from the violet to the red, right? And that's the visible, what we call visible light. But if you go to shorter wavelengths than the violet, you find the ultraviolet. And if you go to longer wavelengths than the red, you see the infrared. And the infrared, basically, that is what we are going to talk about here, and that is important for brown dwarfs, is basically heat. And I'm going to show you how that works. But before that, I'm going to talk about what happens if you zoom in some of the parts of this rainbow. This happens. I promise this is a rainbow from the sun. This is what is called is a rainbow, or a spectral taken by a shell spectrograph. So it's a very sophisticated prism that has a lot of resolution. So you can zoom in basically into the rainbow of the sun and see that the rainbow of the sun is not only colors. It has also a lot of black lines. You see them, right? Thousands of black lines. What are those? Well, those black lines are the fingerprint of the sun. It's like the fingerprint of the star, of the sun or any other star. And it's the fingerprint because each of these lines belongs to a chemical element on the sun, in this case. Each of them. There is no line here that is random. All of them belong to a chemical element. And that's the way we study stars. That's the way we know what is the composition of the stars, because we know, like, All these lines are not in random places. We know that if it's hydrogen, the lines are expected at this wavelength, at this wavelength, at this wavelength, at this wavelength. And we know all of that for all the chemical elements of the periodic table and like all the chemical elements you can think of. And looking for those lines at those specific parts, that's how you know what you have in that star. What is the chemical composition of that star? You can do this with the sun. You can do this with all the stars. This, as you can see, they are all the stars that I show at the beginning of the talk, since the O stars that were the very hot ones, 50,000 K, going all the way to the M stars. And you see how all of them have their dark lines, their spectral lines, and you see that they are all labeled here, each line to which chemical element is corresponding to. Good news. This is, of course, very nice to see because this is the visible light. So we still have like a proper rainbow. So it's something that we can see very easily. But we can also take rainbows and we can also see the spectral lines, these dark lines, in the near infrared. So the near infrared is the part that goes beyond the red, and that is basically connected to heat. I'm going to show you how it's connected to heat. And this is very important because, as I said, most brown dwarfs emit their light in the near infrared. Invisible light. We have two examples here of the meerkats and the crocodile. Invisible light, we see them perfectly, right? Of course, our eyes are designed to see the best in the visible because that's what we are adapted to. We are adapted to see the best under the light of the sun. Of course, we live on the planet Earth. But what happens when we look at these animals through an infrared camera? This is what happens. We know that the crocodiles have, as we call them in Spanish, they are cold blood animals, right? So that means that they usually keep their body temperature similar to the temperature of the environment where they are. That's why you don't have crocodiles in Alaska, well, as far as I know, or in the poles, right? But they are usually in warm places, right? Because they need the heat to be able to function as any living creature. And then the meerkats, they actually have heat, generate heat by themselves. And they are much warmer. That's why you see them so bright here. So the meerkats, they don't emit, well, they emit some, of course, in the visible, but in the infrared, they are very bright. And the humans as well. So if you have ever got a chance to go to any science museum and put yourself in front of the infrared camera, you will see that you are bright in the infrared because you are hot, right? It's the same for the animals. And it's the same for brown dwarfs. Brown dwarfs emit most of the light in the infrared. That's why we need telescope like the James Space Telescope that basically studies the infrared light that comes from the objects in the universe. Okay, so we do rainbows in the infrared. I show you another rainbow. I said that the dark lines correspond to basically to absorption lines, to elements, right? And actually, this beautiful rainbow for scientists, because we love, of course, beautiful plots, but we also love to do science. For us, it's so much easier if you just take this rainbow and basically do an horizontal cut and basically plot what we call the one-dimensional spectrum, which is basically an horizontal cut in this plot. And if you do an horizontal cut, what you would see is that where you have dark lines, there is a dip, right? So, like finding all these lines. So in each dip, you have a line corresponding to one characteristic element, chemical element in the star. This is what we actually use as scientists to study stars, because it's like you have all the information, but in a much more simple plot in a way. So it turns out that not only the spectra or the rainbows of stars of brown dwarfs tell us what they have, but also if those rainbows change with time, that might be also giving us a lot of very, very, very interesting information. So in the case of brown dwarfs, and I'm showing you a real brown dwarf spectra of the Hubble Space Telescope. This is the spectra for Ross 458c, which is also a brown dwarf, and it's also a companion to a star. And you see, this is not just one spectrum. This is many spectrum taken across around 10 hours with the Hubble Space Telescope. And you can see how the spectra change. So each spectra is a little different to the spectra that I previewed before, right? That's why I show each spectra in a different color, and each of them is a little different, which is very interesting. If you compare this super nice spectra from Hubble, from a brown dwarf with a spectra of a planet, this is just for you to show a comparison. This is kind of what you find. So these are, again, our favorite planets, HR 8799, B, C, D, and E. And you see that the spectra that we got for these planets have much less resolution. So you just see, you don't see even a continuum of a spectrum in the sense of that we have just points, right, going across our wavelengths. And of course, the error bars that tells you how is the basically uncertainty on the measurement of your spectra are big, right? So of course they are great because they are real spectra of planets, but we can do so much better with brown dwarfs, right? This is what we got with brown dwarfs. In a spectra like this, we won't be able to see the small variations that happen inside the spectra of the object, right? Like here, we have such a good spectra that we can see the fine variations that are happening across time. With spectra like these ones, we cannot do that because they don't have that much resolution, right? They are not, the error bars are much bigger. So that means that brown dwarfs, again, they are great to study their spectra and also how the spectra of this object change. But it's like, why is it important to study how the spectra of brown dwarf change? Why is that important at all? What does it mean? Well, it means something that is probably going to blow your mind right now. And it's that brown dwarfs have clouds. Brown dwarfs have clouds, as Jupiter has clouds, as Neptune has clouds, as Uranus has clouds. And this is great. This is something that, of course, we kind of expected since we are studying brown dwarfs. But you're gonna see how much similar brown dwarfs are to planets. How similar brown dwarfs are to planets, right? This is, of course, an image of Jupiter that I just put here as a comparison. But I'm gonna show in the next slides how similar brown dwarfs and some of the giant planets look like. And this is what we are going for. First, how do we know that brown dwarfs have clouds? And how do we know how brown dwarfs look like? Of course, brown dwarfs are punctual, right? Why do we see brown dwarfs in Jupiter? Because Jupiter is not a point. It's so close to the Earth that we can resolve the surface of Jupiter, right? Or for Uranus or any of the planets of the solar system, we can resolve their surfaces because they are so close. Of course, with brown dwarfs, we cannot do that. But we have spectra, and we know we have very good spectra, and we see that they change. So what we can do instead is do a simulation of what can be happening on the atmosphere, or how the atmosphere of a brown dwarf could look like. So for that, we take chunks of the spectra. For example, I'm going to take this big peak in this part of the spectra and basically measure how the flux or how the brightness of this part of the spectra changes with time. That's what we call a light curve, right? So now I'm going to show the light curve of one of the brown dwarfs. This is already a brown dwarf that was published a few years ago. And this is how the brightness of the brown dwarf is changing with time. And what happens? What actually happens is that in the parts of the brown dwarfs where we see that there are bands that are actually much brighter than the rest of the brown dwarf, we find peaks in the light curve, right? So basically, we can, if I try to put it again, oops. Let me try to put it again. Basically, again, in the part of the light curve that is very bright, we see like the bright bands. And when it's not that bright, we see that there is no features out there. This is, of course, a simulation that we have done of the surface of the brown dwarf using the light curve, using how the brightness of the brown dwarf change with time. But this is already, I think, very nice, very cool, because actually what we are finding is that this surface of brown dwarfs look a lot alike, like, as I was saying, planets of the solar system, like Neptune, for example. We see that the simulated brown dwarf that I show in the simulated brown dwarf is the one that I show in the right-hand side, and what I show in the left-hand side is an actual image of Neptune, well, video of Neptune, taken with the Keck telescope. And we see that they have similar features in the surface. So they have bands, they have spots, and all of that evolves with time. We have seen, for example, a few weeks ago that actually Neptune is evolving, and like it was not having a lot of storms lately. It was pretty quiet. The same happens for brown dwarfs all the time. But there is even more. If instead of taking this chunk of the spectrum, we take a different part, like for example this one here that has is less bright. What happens if I do another light curve? If I measure well, it happens something very similar. We obtain the light curve, and the light curve give us how the surface of the object could look like. Now, and this is the most interesting part, the light curves done at different parts of the spectra, with different parts of the spectra, don't look necessarily the same. And why is that? Well, what is happening here is that we are actually looking at different depths into the atmosphere of the brown dwarf. So the atmosphere of the brown dwarf is changing, like the cloud patterns inside the brown dwarf are changing as we go down in the atmosphere of the brown dwarf. And this might not surprise you if you like to see images of Jupiter at different wavelengths, like for example, these ones. So you see in the infrared, we see a lot of features. It's very bright. In the ultraviolet, it's not that bright. You don't see that many features in the surface of Jupiter. And it's something in between the visible. That's because the infrared is actually tracing the deeper atmosphere of Jupiter, while the ultraviolet is tracing the upper part of the atmosphere of Jupiter. And if you would do a light curve of Jupiter in these different wavelengths, in these different ranges, it would change. And it would change because the characteristics of the atmosphere change. The map of Jupiter changes with wavelength. Because we are looking at the end, with each wavelength, we are looking at different scales, at different depths in the atmosphere of Jupiter. The same happens to brown dwarfs. A couple of years ago, I was lucky enough to be able to discern the cloud structure, the cloud layer structure of a brown dwarf. This was a press release that we did in 2021 about how are the different cloud layers of a brown dwarf, this brown dwarf specifically, that is actually a pretty warm brown dwarf. And what we can see is like, well, first you can check on the right-hand side the depth in miles from the bottom of the brown dwarf up to the top of the atmosphere. And you see that we found that we had 3 layers of clouds, all of them silicate clouds, so magnesium silicate, phosphoride, and aluminum oxide. And actually, we also check the variability at different wavelengths that tell us that yes, we have these 3 layers of clouds that are producing the changes in brightness that we observe for that specific object. So this is very exciting because brown dwarfs, yeah, they are 3-dimensional objects like Jupiter, like any of the solar system planets that we have, especially giant planets. And of course, since this object evolved with time, and as I said, the cloud structure, the map of our brown dwarf evolves the same way that the Neptune map evolves with time. What we know that is happening is that there is actually weather happening in brown dwarf atmosphere. So there are like rains, there are storms, same way as they happen in the atmospheres of the solar system. But if that was not enough, brown dwarfs also show auroral activity, just as Jupiter does. And this is a specific example that was done for very fast rotating brown dwarf. So if Jupiter has a rotational period of 10 hours, this specific brown dwarf had 1.1 hour rotation period, but it's much more massive than Jupiter. But actually, this brown dwarf show auroral activity. And we know that because this specific brown dwarf was emitting in the radio. And when there is radio emission, that's most likely due to auroral activity in the atmosphere of a brown dwarf, of the brown dwarf. So that's very exciting. That means that brown dwarfs also have auroras. And actually, I didn't have time to have it ready for you, but today NASA also did a press release about auroral emission in another brown dwarf that was discovered with Webb. So brown dwarfs also have auroras. So that we can picture something like this. But of course, this is, again, an artistic picture. So this is all super exciting. Brown dwarfs share so many commonalities. Well, with planets for sure, but also with stars. So coming back to the initial question, are brown dwarfs face stars or Errant exoplanets? So we have brown dwarfs here. And then I'm going to show planets and stars and some of the characteristics that we have for brown dwarfs. So, okay, brown dwarfs. If we take into account the formation mechanism, they look more like stars or like planets. Well, we have seen that it's mostly like stars. But actually, we have also seen that they are brown dwarfs that are together and have a hot star, basically. So they are gravitationally bound to a star. So, well, they might be actually, those brown dwarfs might actually form like planets, although the truth is that we don't know and it's very difficult to prove. But we can say that, okay, we have been like, probably there are some brown dwarfs that form like planets, probably some brown dwarfs form like stars, that's why they have a host star. Fine. This bearing. So we know brown dwarfs have this, and stars have this as well. They orbit a hot star, so only planets orbit a hot star, no stars. Can be, but not the case. Although, yeah, as I have seen, some of the brown dwarfs are isolated at the hot star, right? So in that case, in the terms of what I'm trying to say here is, are they bound to something else or not? So some of them are, some of them are not. Clouds, which is a characteristic unique for planets. Yes, we have clouds in brown dwarf. Another activity, which is something characteristic of planets, we also have. So brown dwarfs share characteristic with both, with planets and with stars. But I think at this point, probably a more useful question that we need to answer is not if they are more similar to stars, to planets, or what's going on, but how can we use brown dwarfs to understand other astrophysical objects? And in this case, I have shown you that brown dwarfs are particularly useful to understand exoplanets atmospheres because they are so much more, because exoplanets are so much more challenging to observe than brown dwarfs. So that's why we should continue studying brown dwarfs, especially now in the era of the JWST telescope that is particularly well designed for studying objects that emit a lot in the infrared, such as brown dwarfs. Actually, there are some brown dwarfs that cannot be observed with other telescope that is not JWST. So for sure, there are a lot of open questions that still we have about brown dwarfs that we hope to be answering in the next decade or in the next 2 decades. And yeah, other than that, the only questions remaining is those that you guys have for me. So thank you very much.
Huh. All right. Well, thank you, Elena. That was really, one of the most in-depth look at brown dwarfs that I've ever seen in my career. Okay,
Thank you.
because you know we've known of brown dwarfs for decades, right?
Right.
But the information sort of goes out in dribs and drabs, and this is a wonderful, comprehensive overview of this field.
Thank you.
And I had actually, I pulled up, I got several questions for you myself, but let me just start with something really basic. But
Okay.
how many brown dwarfs do we know? Okay. Is it tens? Is it hundreds? Is it thousands that we have that we can study in detail?
It is thousands, thousands, more than a couple of thousands now, for sure. So it's thousands. Since we discovered brown dwarfs, we, as I said, the color magnitude diagram or similar to color magnitude diagram of a star that I show in the talk, we started populating those. Like we started doing like a lot of, like for example, the 2-mass survey that was basically looking the entire sky and measuring the colors that I mentioned of all the objects that were discovered, and that's how we started pinpointing, oh, this could be a brown dwarf, this could be a brown dwarf, this could be a brown dwarf, and then all of them were being confirmed. So yeah, in the last 25, well, I guess more 30, 30 years now, we have discovered between 2,000 and 3,000 brown dwarfs.
Wow. Okay, so why don't you stop your screen share?
Right.
And then we've had questions. We've had folks watching on YouTube, and we've had questions in the YouTube chat that Grant has been following to ask about it. Although I am going to ask another question, okay? Because I followed the development of the L dwarfs and the T dwarfs, okay, and it's sort of like a continuation of the stellar main sequence down to the substellar range, right? But you notice this sort of LT dwarf. There's a color transition where it stays at the same brightness, but it
Right.
changes color on this LT dwarf, and so as an astronomer, that first thing that says is, well, all right, there's got to be some sort of physical process that's occurring that causes it to change over in this LT dwarf transition. So can you illuminate that for me?
For sure. So basically, what is happening in there is that L dwarfs are particularly cloudy, but T dwarfs are not. T dwarfs actually they have clouds, but very deep in the atmosphere. So what is happening in that transition is that the clouds are basically raining out to the deeper atmosphere. That's why they are basically disappearing, out of like disappear or like the transition goes from red basically to blue. And that's what is happening in that transition. So the temperatures don't change dramatically, but it's just when all the clouds rain out, and that's why you see this shift in blue.
All right. Okay.
Yeah,
So it's sort of like the development of the changing in clouds in the
it's
atmosphere.
raining. It's
Right.
raining, and actually, what you actually see in those anti-transition objects is that they are very variable. Like their brightness change crazy. We have like some of them that change by 25% or more. And it's because it's just like the clouds are kind of clearing out, and that what happens when they clear out is that you form some holes of like some not holes but like patches on the atmosphere and in different places, and that creates like a lot of variability when you see them rotating.
Okay, great, great, great.
Yeah.
So, Grant, if you would turn on your camera and join us. I know we've had a good number of people watching online. I haven't really been able to follow the question, whether there were questions or not in there, but I think I did see something about deuterium fusion.
Yeah,
You want to start with that question? Because that's kind of fundamental to the difference between stars and brown dwarfs.
yeah, absolutely. So it's actually fits in with what I was going to ask as well. Is
Okay,
I've always heard the same line. The boundary is about 13 Jupiter masses between what would be considered a brown dwarf and what would not. But the secondary, and what I think this person in the chat is talking about, is stars and brown dwarfs produce fusion based on deuterium. However, brown dwarfs stop after the fusion of hydrogen, right? Could you elaborate some more? Okay.
Yes. Brown dwarfs never fuse any hydrogen. Never.
Okay.
Never. That's why they are no stars. So when you see some places brown dwarf stars, no, brown dwarfs are not stars. They are superstellar objects, always. What it can happen, although it has not been demonstrated yet, so from the theoretical point of view, yes, the warmest brown dwarf can fuse some deuterium, but the deuterium is there is not much deuterium in the universe, so they have like a little deuterium from the formation process. They have some deuterium, and they might fuse some deuterium at the very beginning of their lives, but that's gone very rapidly. It doesn't go anywhere. But actually, we are still trying to demonstrate that that's the case, because from an observational point of view, it's very difficult to demonstrate that there is any deuterium in there. It's something that is still needs to be observed. So James Webb, hopefully, will be able to observe any signs of that. But yeah, hydrogen, never. Brown dwarfs never fuse any hydrogen. If they fuse hydrogen, then they are stars.
Gotcha.
And so that just so our audience is clear, what that means is that after a brown dwarf forms, it's at its hottest point there, and then it's from there on in, it's cooling down, right? So it's changing temperature over time, whereas we think of a main sequence star as always as being at a standard temperature or relatively constant temperature, right?
Exactly. So brown dwarfs just are the warmest when they are born, and because they cool down with time, and they just cool down until eventually they cool to the coldest temperature you can have in the universe. Yeah.
But does that mean you can't tell the age of a brown dwarf because you have no idea how long it's been since its formation?
Yes, exactly. Yes, exactly. It's a big problem. The one we have with determining ages of brown dwarfs. My PhD thesis was about that. We are still working about that. And
I would not have guessed.
Yeah, exactly. We don't have a main sequence as stars do, right? Like, a star is burning hydrogen, so we must be between this age and this age. We don't have that with brown dwarfs. So their spectra sometimes can give us some idea of the age of brown dwarfs. Because again, the spectra is changing. It's changing not only because the brown dwarf is rotating and because it has clouds, but it's also changing with time. Because what is happening also is that the brown dwarf is kind of is contracting, right? As they cool down, they contract. So their gravity is changing, and gravity has an effect on the spectra of brown dwarf. In particular, you see that the lines that I was mentioning, the dark lines that I was mentioning, they become darker. So they are deeper lines when there is more gravity. But that method has actually a limit. And for objects, for brown dwarfs that are older than 200 million years or so, we cannot tell. They look all the same. 200 million years old brown dwarfs look the same than 1 giga-year brown dwarf. And only the ones that are super, super old, we can start seeing all the characteristics like low metallicity and other characteristics. But it's a huge problem. And probably what we are going to need to solve it is very high resolution spectra where we can actually see tiny, tiny changes due to gravity or something like this. But it's probably a problem that will be never completely solved.
Yeah. Interesting.
Dwarfs are never going to give up all their secrets.
That's right.
All right, Grant, other questions from the chat?
Yeah, absolutely. We got like 3 or 4.
Great.
So, what mechanism drives aurora on brown dwarfs if they are not associated with a host star?
That's a great question. You guys are very well informed. So we believe that the mechanism that generates aurora in brown dwarfs is actually the storms that they have in the atmosphere. So as we know, for planets of the solar system, what happens is that, of course, the sun is irradiating the planets and of the solar system, like the Earth. That's why we see aurora in the Earth, and they go through the gravitational field of the object of the planet, and basically they interact. The plasma of the sun interacts with the particles on the atmosphere of the planet. Of course, we don't have a host star for a brown dwarf, and if we had it, it would be very far away, because that's the case for most of them. So we believe that the mechanism that has to be producing this aurora is the storms itself that we find in these brown dwarfs. And we believe that might have something to do with the fact that most of the ones that show aurora are very fast rotating, so maybe they have more storms going on. But it's still an open question. It seems that it has to be storms. Also, I know that for some planets of the solar system, specifically for Saturn, there was an article, but only like 2 years ago, saying that some of the storms in Saturn generated aurora. But yeah, again, it's still a mystery that we need to work more on.
Okay, so I got to comment that there was a press release today at the AAS meeting.
Yes.
About aurora on a brown dwarf. And I heard I don't know if it was in the press release or anything, but I heard that there was a possibility that it could be caused by a moon. And if there was a moon orbiting around a brown dwarf, I don't know if it's called a moon when it's orbiting a brown dwarf or what, would
or
that,
a planet.
yes, could that contribute to aurora?
So, Frank, let me insert, because that's a question somebody else has in the chat, is
okay.
If there's something orbiting a brown dwarf, is it a moon? Is it like a satellite? What would it be called? So that's a twofer.
There we go.
You got the best question of all. We don't know. I think I would call it a planet. But again, I think what we are trying to do here is like to classify new things that we know in the universe in things that are familiar to us, like planets and stars. But maybe we need to do a new entire classification, or like new entire group for like brown dwarfs and stuff like, oh, but this is a planet. I would call it a planet in particular, but some people call them moons. The thing is that it doesn't matter. It could happen that there is something orbiting a brown dwarf. It has not been found until yet, a clear evidence. There are some articles that seem, especially one the last year, said that, oh, we found this feature in the light curve on this brown dwarf, and it might be a moon. But the truth is that it's very difficult to tell. And again, we will need something like the GWST to tell us if that's the case or not. It could be another option.
Okay.
But it's interesting. It's interesting that if it's only moons, the brown dwarfs in which we find auroral emission, they are mostly fast rotating. So why only fast rotating brown dwarfs have moons?
No, that doesn't sound right. But yeah, I wasn't aware that there were brown dwarfs that were rotating. You said 1 hour.
Yes.
Wow. I mean that's news to me. That's cool. I mean, I knew Jupiter was 10 hours and such, but as you got bigger, somehow I expected it to slow down, like as you approached like the rotation speed of stars. Right. So
no. Some of them go very fast. Not all brown dwarfs are so fast. So this is the fastest one, 1.1 hour. And there are some that go 24 hours or even more. So it's also a huge span. And that also depends on the age, actually.
Okay.
Gotcha.
What next, Grant?
Next up, is the cooling timescale of brown dwarfs greater than the Hubble time?
We got some good people in our
We have
audience.
some really good
say
chat.
that, okay? For people to just pop out, is it better longer than the Hubble time? Yes. I'm so proud of my audience.
You guys are really well informed. It's only a few giga years. Basically, the cooling. I mean, of course, when they will reach like the zero absolute temperature, I don't think anybody has actually looked into that. But after a few giga years, they are mostly pretty low in temperature. So yeah, no. I mean, still brown dwarfs is something that has a relatively short life in comparison to the life of the universe, right?
Right. I mean, but we when we think about low mass stars, if you think about M dwarfs, I mean, they are projected to stay on the main sequence longer than a Hubble time, right? And so I think that that's sort of the spirit in which that question was asked. Once you go down below M dwarfs and you get to the L dwarfs and T dwarfs, they won't stay as L dwarfs and T dwarfs. They'll for longer than a Hubble time. So you sort of reach your maximum lifetime on the main sequence with the M dwarfs, and then it's going to decrease because it'll take a long time for those to fade.
Yeah. And actually, if you think about it, okay, in stars, you can define the life of a star, right? In brown dwarfs, there is no such a thing because there is no main sequence. There is no, there is no hydrogen burning. So they are just there. They don't have like a life, right? Yes.
Or begs the question of whether it's better to burn out or fade away, right? And brown dwarfs definitely just fade away.
For sure.
So I've got two more, potentially just one, depending on our time, Frank.
Okay. We're okay. We're okay. We got time for two.
Okay. So secondary, kind of to what we were talking about first, you can't measure anything based on the amount of deuterium that has been burned or is or was present in the star. It's non-detectable, or it burns off so quickly in the early life of a brown dwarf, it just isn't measurable.
Right. So it actually is, I think what's happening, first it goes really fast, but we actually know young brown dwarfs out there in which they could potentially still keep some deuterium. The thing is that the feature that corresponds to the deuterium on the spectra is actually rather small, tiny. So you need to have a very high signal to noise spectrum to be able to measure that feature. And until now, only James Webb can do that. So that's the problem. I'm sure there are astronomers looking into it.
All right. So
actually, Grant, I want to jump in with one more question, because when you looked at those peaks and you saw the changes in just one brown dwarf spectrum, there are several peaks that you could measure in terms of the changes, right? Do each of those peaks correspond to particularly, or at least a supposed ice crystal structure in the brown dwarf, or a cloud composition structure in the brown dwarf? Because we're used to thinking of the ammonia ice or the magnesium or the other different elements in these crystals in the atmosphere.
Right. Yes. So in the spectrum that I show of the brown dwarf, what you could see, basically on the peaks, on the very top of the peaks, you have like the methane absorption. The Hubble spectra is a great spectra because they have very high signal to noise, so the errors are super tiny, so it's great. But the resolution is not that huge. For that, JWST is much better. But still, like the big molecular absorptions you can see. So the big absorption that you see there is water, and then there is also methane next to the water, basically in the spectrum. And then if we have higher resolution, we should be able also to see that is potassium, that there is sodium, and a longer wavelength. So it's something that you will see with NIRSPEC and JWST. You will see CO absorptions. You will see more methane, and probably if you go to the more mid-infrared, where MIDI onboard JWST is observing, you will also probably see some silicates at 10 microns and things like this. So it's full of spectral features. Yeah, I should have shown you the spectral features, but yeah.
No, I mean, it's just great because not only are we able to say, hey, there are clouds on these brown dwarfs, we're able to say what the composition of those clouds are
Exactly.
and the changes in those clouds. And that's just really cool, you know?
Exactly. It's amazing that we have so much information from this object. It's amazing how we can get all this information.
All right. You said we have one more question, Grant?
Yep. One more question, and I think we'll tack on the second part to this. What would be some recommended reading material on brown dwarfs for our audience? And what's your favorite observation that you've had this last year?
Oh my God. Okay, I'm going to start by the second.
Okay.
Because JWST is doing awesome observations of brown dwarfs. There was a press release earlier this year, 2023, that they showed the entire spectrum of a brown dwarf. Actually, the brown dwarf that I was mentioning in the talk, that was a companion to the binary star. We have a near spec high resolution spectra and a midi high resolution spectra, and it was covering from 1 micron to 20 micron and a high resolution. So we could see all the spectral characteristics of the spectrum, like very finely with high resolution. And for me, after more than 10 years in the field, it was mind-blowing seeing all the spectral resolution of those spectra and the wavelength coverage that it has. And also that particular object is highly variable. It's actually at the famous LT transition that we were talking about, and it shows a variability of 20%. So it has clouds, and it has the clouds are varying a lot. So it's super interesting object that we continue actually to work on, to study, we are getting more and more data from JWST, and we are looking forward to study in detail, how all those tiny special features are changing with time, because that's going to tell you how the atmosphere is changing with time at different depths. So we are going to be most likely to be able to do a 3D map of this object. So it's mind-blowing, and that's for me my favorite observation so far from 2023.
I love it.
And what I love about that, Elena, is that it showcases how much new science comes from the spectra capabilities of Webb. Yes. No offense to our audience, but the public loves their images, right? And they go gaga over the images. But, what you've shown here tonight shows you why they should be going gaga over the spectra as well. Because when you can get that kind of detail in the spectra, you really can learn so much more.
Exactly. Yes, exactly. So, of course, the images have a lot of information. They are amazing. I agree. I love them too. But the spectra is what really gives you all the little tiny details that all astronomers are interested in, because it tells you about the chemistry that is going on, the physics that is going on. So you kind of see the object on a 3D, right? It's so much information. It's amazing. So yeah, the spectra are for sure really valuable, and for astronomers, that's probably the most important piece of information that we get from any telescope.
All right. Was there a second part to that question that didn't get answered, or because she said her favorite?
Reading material. What would you recommend the audience?
Are there public level books on brown dwarfs out there?
Yes, so there is a book that was published, but it was already 10 years ago, by an astronomer that was called Vicky Jorgens, and she wrote this book. Well, she and many other brown dwarf astronomers, because it was the 50th anniversary of brown dwarfs. So brown dwarfs were discovered in 1995, but the first time somebody made the theory that this should exist was in 1965. So it was for the 50 years of Brown Dwarfs, for 50 years of the anniversary, that she wrote this book. It's kind of limited edition, but I've been able to find it on Amazon. And it's, I believe it's called 50 Years of Brown Dwarfs. So it's like a pretty good book and has like a very good overview of everything that has been happening on brown dwarfs since they were theorized in the first place and until back in 2013. But of course, you know that the literature is all on the internet, so there is like the astronomical database of articles, and there you can find all the articles, the new articles that come up. And just by tapping brown dwarfs, and they will show you everything, and you have a lot to read. I send all my PhD students there to do that all the time.
I love it.
All right, well, thank you so much. You know, brown dwarfs are, you know, a bit of an unexplored country, you know, in terms of thinking about them, and that although we've discovered some for, you know, for 20, 30 years now, even for an astronomer like me who, you know, feels like he knows a lot about the universe and lots of different things because I do outreach, you filled in a lot of gaps for me. So I want to thank you myself.
Thank you. I'm glad that you enjoyed the talk.
All right. So next month is something to be announced. I will have that up on the website in the next week or two. Until then, thank you all for joining us and have yourself a wonderful day.